this video is about Core Practical 9 in the Further Mechanics section of the A-level specification. It's also specification point 98 for the home A-level, the UK A-level, and 82 for the international A-level. What tends to happen with these is that you're expected, of course, to do the core practicals. There's a minimum expectation of the number of core practicals that you do, but you're also expected to learn practical skills and techniques from this, from each of the core practicals that you do. So what I'm going to do is I'm going to go through this core practical and then use this to demonstrate some of the techniques. And each of the core practicals that I'll cover, I will use different ones to demonstrate different techniques. I'll also be creating a set of videos on just the practical techniques, calculating uncertainties, plotting graphs, and linking them to equations, things like that. Okay, so let's look at this. We have to investigate the relationship between force and change in momentum. And the further mechanics practicals, or certainly the year 13, the second year of A-level practicals, tend to be a little bit more involved than the ones that you might do in year 12. So with this one, we have to set it up like this, and it takes most of the time to set it up. So the idea is that you have a trolley, and it's attached to a piece of string and a pulley, but the string goes over a pulley and the masses are attached to the end of the pulley. The idea is that you have the string taut. So you start it off with it taut, and you mark the position of the trolley when the masses just touch the floor. And this is the exact position where you want to put your light gate. So what you want to be able to do is you want to be able to measure the speed of the trolley after the masses have accelerated it. And so this is going to measure our V, and it's going to be V is distance over time here. And so your light gate is set up to measure time. What you then do, once you've got it all lined up and it's all perfectly matching up with the masses on the floor, etc., you pull the trolley backwards to this point, and then you release it. Now, you want to try and make that point as far back as possible, and I'll tell you why in a moment. You pull the trolley back and you release it, and you use the stop clock to time how long it takes the trolley to go from the release point to the light gate. Okay, what we want to do is measure force, because we're investigating the relationship between force and change in momentum. So in order to measure force, we are going to use, these are the masses that are causing, their weight rather, is causing an acceleration. So this is our force. So our force here is m times g. So the first thing you're going to have to make note of is the masses there. Then the force acts for the time that is recorded on the stop clock. And when we multiply force times that time, we're going to get the impulse. The next thing we need is the final velocity of the trolley, like we said here, and that is using the length of the interrupt card divided by the time that you read off the stop clock. The velocity of the trolley. Then we're going to use that to find the final momentum of the trolley, and to do that you need a balance with which you measure the mass of the trolley, multiply that by V, and that's going to be your final momentum of your trolley. Obviously its initial momentum is 0 because you've stopped it and released it from this point over here. The impulse then is going to be F times T, or mgt. That's equal to the change in momentum, so our mgt should be equal to m times v. And that is the relationship that we're exploring here. So what are we going to change and what are we going to measure? Well, we are going to change the m, the masses, right there. So you're going to start with the lowest mass, and you're going to increase those so that you get greater acceleration, greater change in momentum, and you're going to see what happens. If we look again at our relationship over here, we're going to rearrange this so that it's equal to m times t is equal to capital M over g times v. This is in the form y equals mx. So this is what we're going to be changing and measuring. And we're going to be making sure that we can get a straight line through the origin, and from that straight line through the origin, we are going to use the value of g to establish how accurate and valid our experiment is. So we're changing m, we are measuring capital T, that is the time taken on the stop clock, and we're calling it capital T to distinguish it from the small t, which is the time you get on the light gate. So we're going to measure t and we're going to measure small t in order to calculate v. Capital M is constant, so our gradient here should be a constant value giving us a straight line because capital M is constant and obviously g is constant. This is the graph we're going to plot. mt on our y-axis, v on our x-axis, remembering that our equation is mt is equal to capital M over g times v, and there's our y equals mx. So obviously our gradient is going to be capital M over g, meaning that small g is going to be equal to m over our gradient. And I'm deliberately not using small m for our gradient here so that we don't get confused between all of the m's. At the end of the experiment, you should have at least 6 values that you can plot on this graph, and hopefully you're going to have a graph that is a straight line that passes through the origin. With this practical video, I'm going to be focusing on calculating uncertainties because it's quite involved here, and so it gives a good example of compounding uncertainties. When you're looking at uncertainties, you need to think about what quantities did you actually measure. So let's have a look and see what did we measure here. And we need to look at the uncertainties in those measurements. First of all, we measured the length of the card. Now, usually with light gates, the default setting is 10 centimeters for the length of the card that's put into the system. So it's a good idea when you're doing this just to cut a length of card that's 10 centimeters. You do get plastic ones that come pre-cut to 10 centimeters, but if you're having to use cardboard, then just cut it to 10 centimeters so that you don't have to adjust the settings. Now we only measure the length of the card once with a meter rule or some form of ruler, and therefore we're going to have to use the method for finding the uncertainty using plus or minus half the smallest scale division. So suppose your card is 10 centimeters long. That means that it's going to be 100 millimeters plus or minus half a millimeter, because 1 millimeter is the smallest division that you get on a meter rule. So that's our first bit. Generally, we will turn that into a percentage uncertainty, so your percentage U is 0.5 over 100 times 100, which of course is 0.5%. That's our first measurement. The next measurement we made were the masses, causing the acceleration. Now, usually these come as either 50 gram or 100 gram slotted masses that you put on a hanger. And unless you actually put those masses on a balance and measure them individually, we just assume they don't have any uncertainty. So we're going to go ahead here and assume you use the slotted masses and that they don't have any uncertainty. In reality, they do have a small uncertainty. Usually they come with a plus or minus 5%, but we're going to ignore it for our purposes here. Number 3 was the stop clock time, given the symbol capital T. This is going to be a big one because any time that you have to use a stop clock, you are having to consider reaction times in this. And so times using a stop clock are always a huge source of uncertainty, especially when it is such a short time. So if we go back up to our experiment, I said to you at the time, try and make sure that you have as long a distance between the light gate and the start position as you can. And the reason for this is because you are having to start and stop your timer, measure the time between those two distances as the trolley travels. And as you add masses on the trolley, and it goes faster and faster, that's going to be increasingly difficult to measure. So if you can maximize this distance from start to light gate, that's going to minimize the errors that are going to creep into your timing. The other thing about timings like this, because you know that there's going to be quite a lot of estimation in it, you should always do repeats for reliability and to assess your precision. And if you go to my playlist about working as a physicist, you'll find definitions of these actual terms given by the exam board, what they're expecting you to know, and how they're expecting you to apply these terms. The other thing we always do is we always take an average, without including any anomalous results in that average, and that average then improves the accuracy, because it reduces the effect of random errors that creep in. Now, obviously, we cannot use the smallest or half the smallest scale division here, because on a regular stop clock, it might measure to 100ths of a second, and you're not purely about to suggest that half of that is the uncertainty in your timing. You cannot do that. So here we have to do repeats and take an average, because we have to be able to assess our uncertainty from that. So we would use half the range of our repeats to find our uncertainty here. Realistically, that does not include any issues with reaction time starting or stopping. So let's suppose then that we have a set of times like this. Three repeats is fairly standard. If you get a lot of variation, you might be better off doing even more than 3 repeats. The average of these our uncertainty here is going to be plus or minus the largest value minus the smallest value divided by 2. And that gives us 0.32 seconds. And again, I'm matching the decimal places here. Calculate our percentage uncertainty then, we say 0.32 over our average, 2.33, times 100, giving us a very large uncertainty of 13.73%. This is the issue with timing, especially when times are very short like this. The fourth thing that we measured is the time from the light gate. This is likely to have a very low uncertainty, and therefore a very low percentage uncertainty. You can do the same process and look at the repeats that you get from the light gate timer, find half the range of the repeats, put it over the average, get yourself a percentage, but for now we'll call it, let's say, 0.1%, so it's almost insignificant. Now that we've got all of the percentage uncertainties from the quantities that we measured, what we want to do is we want to find what is the uncertainty in our gradient at the end of this, because this is what we were after. We were trying to find what the uncertainty in our gradient and even our uncertainty in the value of the gravitational field strength. So we have to compound our uncertainties. So when you calculate with measurements that have uncertainties, you have to start compounding them, and this is the reason why we calculate the percentage uncertainty. So we're going to look at, first of all, what is the percentage uncertainty and therefore the uncertainty in the gradient that we got in our graph at the top there. So the gradient is produced by the change in y over the change in x. That means that for us it is mt over v, because that's what is on our y and on our x-axis. So we have, in our m's, we've assumed that it's 0%, because they were supplied masses. Our t was our time on the stop clock, and that's our big one, 13.73%. Our v is, remember, the length of the card over the time on the stop, on the light gate. And the percentage uncertainty in the length of the card was 0.5%, and the percentage uncertainty from the light gate was 0.1%. And note that if you multiply or divide quantities with uncertainties, you add together their percentages. So that gives us a total then for V of 0.6%. And these are our three quantities that have gone into calculating our gradient. So to find the total uncertainty in our gradient, we simply add these percentages together. Giving us a total percentage uncertainty of 14.33%. This practical generally produces very large uncertainties because there's only so much bench that you can have that you can pull your trolley back to, and therefore our timings tend to be relatively short. The next question you might ask yourself is the experiment valid? In other words, did it measure what it was supposed to be measuring? And in this case, we were getting the G, the value of the gravitational field strength from our gradient. So did we actually get the gravitational field strength considering the uncertainties that we have acknowledged that we have in our experiment? So how are we going to do that? Well, there are two ways about it. Method A is to use our 14.33% uncertainty to find the upper and lower bounds of the gradient. So for example, if our gradient was calculated as 0.125, and I'm just ignoring the units deliberately at the moment, we're going to find 14.33% up from that and 14.33% down from it. Okay, now we know that our gradient, and I'll use small m here, is equal to the mass of the trolley divided by g. So let's allow the mass of the trolley to be about 1.1 kilograms, that's approximately what they are, and then use our upper and lower gradients, put them in as values here, find out what value those upper and lower limits are going to give us for g, and see if the actual value of g falls between those. And if it does, our experiment is valid. If it does not, it is invalid. This is our range of g that we got from our gradients. And as 9.81 meters per second is our actual value of g, and it does fall between these two, then our experiment is valid. The second, and perhaps slightly faster way of assessing the validity of an experiment is to use something called the percentage error. Again, we know that our gradient is capital M over g, and we know that m is 1.1 kilograms. If we go back to our original gradient as being 0.125, that gives us a value for g at 8.80 meters per second squared. What we need to find now is what is the difference between that and the real g. And that's what's called the percentage error. And then we're going to compare that percentage error with our known uncertainty. So we have said we are not certain about this 8.8. We have said 8.8 is our value, but of course we've got a 14.33% leeway in this. So if this is less than 14.33% away from real g, then our uncertainty encompasses that error and our experiment is valid. So let's try it. To find the percentage error, you find the difference between the known value and your value over the known value times 100. Now we compare our 10.29% with our uncertainty. So 10.29% error is less than our 14.33%, which was our uncertainty. Therefore, our experiment is valid. Again, because we have said that our value of g is 8.80 meters per second plus or minus 14.33.